This video is about the MG1 infinity queuing model. So for the interarrival times, the exponential distribution is often suitable, but for the service times, it can be that this distribution is not very appropriate. And in that case, we can use the MG1 infinity queuing model with an arbitrary distribution for the service times. So we still have interarrival times that are exponentially distributed, and we now have an arbitrary service time distribution with a certain mean and a certain variance. We have a single server, and we assume that that the queue capacity is infinite. And then we define rho as lambda multiplied by the expected service time, and this needs to be smaller than 1 in order to have a steady state. So for instance, if 2 customers are arriving per hour, and then the mean service time should be less than half an hour in order to have a steady state solution. So that makes sense. We have, of course, that P0 is 1 minus rho, and we also have the following that can be derived for the MG1 infinity queuing model. So the following formula for the expected time in the queue. And then, of course, if we have one of the performance measures, we can also calculate the others. Also maybe good to mention is that WQ and also the other performance measures are increasing in the variance. So if the mean service time remains the same, but if the variance increases, then all those performance measures go up. So not only the mean of the service time is important, but also the variance. And if the variance is higher, then everything becomes less predictable. So then all those performance measures are going up. We are going to consider an example, an MG1 infinity queuing system with 12 customers arriving per hour, and each customer requires a service time that follows now a Weibull distribution. The exact properties of the Weibull distribution are not that relevant. It's only the mean and the variance that are important. So here we have a mean of 2 minutes and a standard deviation of 1 minute. And now the question is to determine the mean number of customers in the queue, and also to determine the mean time that a customer has to wait. So let's do that. So what we have here, let's write that down, and we should of course first choose the time scale. You can choose for hours, you can also choose for minutes. If we choose hours, then we will get that lambda is equal to 20. That's the number of customers that arrive per hour. Then the expected service time. We have an expected service time of 2 minutes. If we work in hours, then it's 1 over 30 hours. We have a standard deviation of 1 minute, and 1 minute is 1 over 60 hours, and the variance is the standard deviation squared. So this is then equal to 1 over 3600. And then we can calculate the mean waiting time. So WQ based on the formula that we have. So we get lambda is equal to 20, and then we multiply that by the expected service time, which is 1 over 30 squared, plus the variance is 1 over 3600, and then we divide that by 2 times 1 minus lambda times the expected service time. So this is the expected waiting time. Let's see what we have. In the numerator we have 20, then it's 1 over 900 plus 1 over 3600, that's 5 over 3600. Can be written as 5 over 3600 divided by 2 times 1 over 3, and that is equal to 100 divided by 3600, and then instead of dividing by 2 over 3, we multiply by 3 over 2, and this is equal to 1 over 24, and we then talk about hours. So the mean waiting time is 1 over 24 hours. We can also write it in minutes, of course, and then we get 2.5 minutes. So this is the mean waiting time. Second question is, what is the mean number of customers in the queue? Or that's basically the first question, but we first need to calculate the mean waiting time before we are able to calculate the mean number of customers in the queue. And for the mean number of customers in the queue, we have Little's formula, one of the two. So it's LQ is lambda times WQ. And then we get 20. It's in hours, so we use the WQ also in hours. So it's 1 over 24, and that gives us 5 over 6. So 5 over 6 is the expected number of customers in the queue. So on average we have 5 over 6 customers in the queue, and we have a mean waiting time of 2.5 minutes.